This lesson is for chapter 20.3 in the GCSE textbook, which covers tree diagrams. So there's two different sorts of diagrams we're going to look at today. First thing we're going to look at is something called frequency tree diagrams. And these are used to show the outcomes of two different events. Then we'll go on to tree diagrams, which will be the majority of the lesson. And these are also used for two separate events, but rather than showing outcomes, they show probabilities. And what we can do is make use of these tree diagrams to calculate probabilities for multiple events. You can have even more than two events if you want to. And we're going to also look at independent and dependent events to see if you understand the difference between those, both of which you can use tree diagrams for. Okay, so first of all, let's have a look at frequency trees. So if you have your exercise books out in front of you and you write your title, and let's write a few notes on frequency trees. So you can use a frequency tree to show the outcome of two events. Now you'll see in a moment why they're called trees. They're made up of branches like a tree, and what you do is you write numbers along the branches, and these numbers represent the frequencies. So probably the best way for me to show you what one looks like is through an example. So here's the example written out in words. So what I'd say, if you can just pause the lesson and write down that example, and then as soon as you're ready, click play again. Okay, so we're talking about a factory with 300 workers. Workers are either skilled or unskilled, and then the skilled and the unskilled workers either work part-time or full-time. Okay, so what we've got to think about here is the sort of things that we are going to represent on this diagram. So the first thing we're going to represent is branches to show whether the workers are skilled or unskilled. So this is our first part of it that we're going to draw like that. So what we do is we write at the end of the branch what is either what outcome or what thing we're looking at. So our workers can be skilled or they can be unskilled. So we draw two branches because there's two different types of workers. Okay, and at the end of the branches we say what those types of workers are. Now here's where we represent the numbers along these branches. Okay, so 100 of them are skilled, so we'd write our 100 there. And it says the rest are unskilled. Well, it's not too difficult to work out. If there are 300 in total, 100 are skilled, then that means that we're going to have 200 unskilled, which we'll write along there. Okay, now we're going to continue building up our tree with some more branches. Both the skilled and the unskilled workers can then be broken down into two more categories. First one is part-time, I'm just going to call PT, and the second one is full-time, which I'm going to call FT. And again, we can write some numbers along those branches because from the skilled workers, 25 are part-time. So we can fill in the full-time because we know there's 100 in total, 25 are part-time, 75 are full-time. And again, we'll do the same thing for our unskilled. They can either be part-time or full-time because you can see how we're sort of categorizing things here. All right, and then with the unskilled, do read it carefully. It says 120 are full-time, so the 120 goes down here. So how many are part-time? Well, there's 200 in total, 120 full-time, so that makes 80 part-time. So that is what a frequency tree would look like. You can see it's got different categories, it's got branches, and then along the branches we write frequencies or numbers of things. Now what we can do is we can read some values off of this to help us answer some questions. So the first one says how many part-time workers are there altogether? So what we need to do is we need to identify on our diagram which are the branches that represent part-time. So you can hopefully see, well, we've got those that are part-time and we've got those that are part-time. So altogether, part-timers, bit of working, 25 plus 80, which is 105. Okay, and then part C, if a worker is chosen at random, what is the probability they are full-time? So let's identify our full-time workers on our tree, on our frequency tree. We've got 75 and we've got 120. Okay, so the full-timers in total are 75 plus 120. Okay, which is 195. Probability of being full-time? Well, that's going to be how many are full-time? 195 out of how many are total? It says it in the question there, 300. So 195 over 300. Put it in your calculator and that cancels down to 13 over 20. And I'm just going to leave it like that. Okay, so that's what a frequency tree looks like. So what you'll notice is it looks like a tree, but it's got numbers along the branches. So that's an important difference to the next thing we're going to look at, which is tree diagrams. They do look similar, but they have different things written along the branches. Okay, so let's have a look at what the difference is there. So the difference with the tree diagram is that rather than showing frequencies like a frequency diagram, it has probabilities along its branches. Now there are some rules for our tree diagrams, so I think before we start drawing some, what we'll do is we'll just have a look at what the rules are for drawing them. You write these down and then you can remember them. Okay, so we draw branches in a very similar way to what we did with our frequency trees. Okay, and at the end of each branch we write our outcome. Okay, and you have one branch for each different outcome. So when you start drawing it, the first thing you're going to think about is how many different outcomes can I have for my first event, and that's going to tell you how many branches to start with. Okay, rather than writing the frequencies along each branch, you write probabilities along each branch. Now you can write them as fractions or you can write them as decimals. It really depends on how the question is worded. So we'll have a look at each of those types. Now the important thing is a set of branches for one of these diagrams should represent all of the different outcomes for an event. You know, if you look at all of the different outcomes for an event, then all of their probabilities should add up to 1. If they don't, you've missed one of the outcomes. So when you're writing your probabilities on the branches, that's quite a good thing to remember, so you can make sure that you've not missed anything out. Okay. Now, to use our tree diagram to find probabilities, you'll notice in a moment what we're going to do is as we travel along our branches to get to the outcome we're interested in, we multiply any of the probabilities that we come along. And the reason for that is when you multiply probabilities, you're saying the probability of that happening and the probability of that happening. Remember, with probabilities, something and something is a times. And do you remember last lesson we were doing something or something, and that gave you a plus, okay? So you multiply along the branches, and if there's a number of different ways of getting the thing we're interested in, then you can add up those different ways of getting it. Okay, so just make sure you've got that written down in your notes, but I think it will all become a lot clearer once you've had a look at a few examples. So do pause now if you need to, otherwise we're going to move on and have a look at our first example. Okay, so here's our first example. So what I want you to do is write that down, pause it if you need to, okay, and we're going to draw a tree diagram to represent that. So you can see we've got two separate events going on here. The first event is going to be what happens at the first set of lights, and the second event is going to be what happens at the second set of lights. So when we first start drawing our tree diagram, the first thing we're going to think about is when we get to the first set of lights, what are the different outcomes that can happen? And that will tell me how many branches I need. Okay, so hopefully you've thought to yourself, okay, at my first set of lights, two things can happen. She can either stop or she doesn't stop. All right, so that's my two different outcomes, hence my two different branches. So What I'm going to do then is write the probabilities along those branches. We're given in the question the probability that she stops is 0.3. So what's the probability she doesn't stop? That's right, it's going to be 0.7. Here's my quick check. If I add them, do I get 1? Yes, I do. So that's the first part of my tree diagram drawn. Now I'm going to continue with more branches off of these two, thinking about what happens at my second set of lights. Okay, so again at the second set of lights, I can have two different outcomes, stop or don't stop. So I draw those on again. Let's write the probabilities on them. Okay, probabilities are slightly different for this one. So I've got 0.2, she stops. So what's the doesn't stop? That's right, 0.8. Now notice, because I've got my other branch from my lights 1, I must then repeat those on that branch, and the probabilities are going to be the same for those. Okay, we can now start using our tree diagram to read off all of the different possible outcomes by going along the branches. So let's look at the first possible outcome. The first possible outcome going along those two blue branches is stops at the first light, stops at the second light. Do you remember what I said? How I work out the probability is I times the probabilities along the branches. So the probability that she stops at the first and stops at the second, 0.3 times 0.2, which is 0.06. Okay, so multiplying as I go along the branches. Let's look at the second one. The second blue branches, that stops at the first, doesn't stop at the second. So again, let's write the probability down for that. Stops, doesn't stop, 0.3. Notice timesing, because it stops at the first and doesn't stop at the second. Times them together and you get that. Let's do the last two. That's a doesn't stop and a stop. Okay, doesn't stop and a stop, 0.7 times 0.2. And then the last one doesn't stop at either of them. Okay, and I've got 0.7 times 0.8, which is 0.56. Now, there's a question they're going to ask us. What's the probability that she has had to stop exactly once? So look at the 4 different outcomes that we've got here. How many of those are we interested in? She has to stop exactly once. Okay, so that's stop once, don't stop once. Which ones are we interested in? That's right, it's those 2 in the middle. Now, for her to stop exactly once, it can be stop, doesn't stop, or doesn't stop, stop. So to get the answer for that, what we do is we take those 2 pink box probabilities and we add them together, because both of those fulfill what we're interested in, which is has to stop exactly once. So we add them together to get our answer of 0.38. Okay, so quite a lot going on there, but all you've got to think about when you're drawing your tree diagrams is making sure you think about what are the different outcomes I can have for my first event. That gives you your branches. Write what the outcomes are at the end of the branches and then pop the probabilities on. Make sure the probabilities on the sets of branches add to 1, and then you add on to the end of those, okay, the different outcomes and the more branches for event 2. Okay, right, let's have a look at another one then. Okay, so again, pause this and write down that example. So we've got a bag containing 2 red and 5 blue counters. So a counter is taken out, its colour is noted, and then it's returned to the bag. That word returned is in bold because that's important. It would be a different situation if we didn't return it, and we're going to have a look at one of those in a minute. Okay, so draw a tree diagram. So you're going to return it to the bag and then pick another one. Draw a tree diagram showing the probability of each outcome. So our 2 events that are going on then are choosing the first counter, okay, and choosing the second counter. So to think about how many branches we need for our first event, what are the different outcomes for choosing the first counter? Well, we can either have a red one or we can have a blue one. Okay, so I'm going to call that and just put underneath it choosing the first counter. Okay, so that's going to say what that first event is. Now, what I'm going to do along these branches is I'm going to put the probability along those of choosing a red counter. So you have a look at the information in the question. What is the probability of choosing a red counter? Well, the bag has 2 red and 5 blue, so the probability, much easier to use fractions for this one. The probability is going to be 2/7 for choosing a red one, and 5/7 for choosing a blue one. Again, double check they add up to 1, they do. I'm going to now add on branches for my second event. My second event is choosing my second counter. So again, the branches are going to be the same. It depends what the question has in it as to whether they're the same branches or they're different branches, okay? For this one, they are the same branches. And this is my second counter. Now, because I've put that first counter back in, the probabilities for these are actually going to be the same as for the first branches. So they're going to be 2/7, 5/7, 2/7, and 5/7. Okay, so now what I can do along the ends of here is I can write the probabilities for each of the outcomes. So travelling along those real top branches there, that's going to give me the probability of a red and a red. Do you remember what you do? Times them together. 2/7 times 2/7. Now this could be non-calculator, so make sure you can times fractions, times the top, times the bottom. Okay, second one, probability of a red and then a blue. So that is going along these branches, red and then blue. So I multiply the probabilities as I go along the branches. Oops, sorry, that's a bit funny. 2/7 times 5/7, which is 10/49. Third set is going to be blue first counter, red second counter. Okay, so 5/7 times 2/7, again times the top, times the bottom. And then my last one is choosing a blue first counter and a blue second counter, and that's 5/7 times 5/7, 25/49. Okay, now this has covered all of my different outcomes, so you can just as a quick little check that you've not done anything wrong, all of these should all add to 1, okay, because this is all of my different outcomes from my 2 events. So a quick double check to make sure it does add up to 49/49, confirms that it does. Let's read what the question says. Now the question says, what is the probability of getting 1 red and 1 blue? So we need to have a look at our outcomes to decide which of those fulfill that criteria. 1 red, 1 blue. It's going to be that one, 1 red, 1 blue, and that one, 1 red, 1 blue. So to work out either of those, because either of those are fine, what we're going to do is we're going to take that probability which we were interested in, and we're going to add it to this one, because remember it's a probability of red blue or blue red. So I take them and I add them together, okay, and I get 20/49. And if that does cancel down, then cancel it down, but that one actually doesn't. Okay, so that's what your tree diagrams look like. Notice I've got probabilities along the branches. In this question, much easier to leave them as fractions. In the previous one, they happen to mention decimals. It really doesn't matter which. Okay, let's talk about independent events then. Do you know what independent events are? Maybe, maybe not. Okay, you need to write this down. So if A and B are independent events, then what happens with the outcome of A does not affect the outcome of B. Okay, so if A and B are independent, then the probability of A and B should be the probability of A times the probability of B. Now let's have a look at the previous tree diagram that we drew. That was two independent events because when we chose our first counter, we then returned it to the bag before we chose the second counter. Okay, so whatever I chose for my first counter didn't affect the probabilities for my choosing my second counter. So you'll notice the branches for my second counters were identical. So there was no difference as to whether I chose a red one first or a blue one first. Okay, let's compare that then to this next example that we're going to have a look at, where we got dependent events. Okay, so this is a sort of an exam style question. They quite often in an exam actually give you a sort of structure of a tree diagram and ask you to fill it in. So if you can write down the question, notice this is dependent events. Why is it dependent? Well, there's some chocolates in a box. My first event is Rob taking one and eating it. Okay. And then my second event is then Alison taking one and eating it. Now, think about it. If Rob takes a chocolate out and eats it, what's going to be left in the box is going to be different depending on what chocolate he picked. So Alison's probabilities that we're going to look at on this diagram are going to be different depending on whether Rob chose a milk one or Rob chose a plain one, because there'll be a different amount of chocolates left, if that makes sense to you. You'll see now if we fill in the probabilities. Okay, so I'm going to fill in this top probability first. Probability that Rob chooses a milk chocolate. This is what we've got to start with: 6 milk, 4 plain in a box. So the probability of choosing a milk is 6 out of the total, which is 10. Now don't worry about cancelling it down. Quite often when you're multiplying things together and adding things together, it can be easier just to leave the fractions in that form, and the examiner is actually fine with you doing that. Okay. What's the plain chocolate probability for Rob? 4 out of 10. Okay. Now here's the bit where you've got to think about this carefully. All right, you've got to think about this carefully. Now, Alison is now going to choose her chocolate. Okay, Rob has eaten a milk chocolate. So what's the probability that Alison will choose a milk chocolate? Well, the first thing to say is the probability is going to be out of how many chocolates there are in the box. And for all of these, Rob's eaten one. Okay, so all of these probabilities are going to be out of 9, aren't they? Because he's eaten one and there's only 9 left. Okay, let's think about Alison then. She's going to choose a milk chocolate. How many milk chocolates are left? Well, there were 6 to start with and Rob's eaten one, so there's 5. Okay, happy with that? 5 left. Notice the denominator has gone down by 1. That's why actually leaving this in an unsimplified form can help you, because you know you need to take the denominator and you need to subtract 1 from the denominator because there's 1 less chocolate in that. Plain chocolate. Now you can either think about how many plain chocolates there are. Well, he's not eaten any of them, so there's still 4 left. Also, you can double check these 2 probabilities here, remember, because that's the both branches there, they should add to 1. Okay, so always do a double check that they do, that you've not done anything wrong. Okay, let's go down to the second branches there then. They're going to be different probabilities because for these second branches, Rob has eaten a plain chocolate. So how many milk chocolates are left? Well, there's still 6 because he hasn't eaten any of those. Okay, how many plain chocolates left? Well, he's eaten one of them, so there's going to be 3. Again, do that double check that they add to 1. And they do. So notice with that, because it is dependent events, or what's called conditional probability, okay, the probabilities on these second branches vary because they depend on what Rob chose for his chocolate. That's why they're called dependent events. Now, we use the tree diagram in the same way as we have for previous ones. What does part B say? Work out the probability that there are now exactly 3 plain chocolates in the box. Okay, right, well, for there to be 3 plain chocolates in the box, we need to have eaten exactly 1 plain, don't we? Because we started with, here it is, we started with 4. So which of these then are eaten 1 plain? Remember, this top one is milk. Well, that's not eating a plain one. This next one is milk plain. Well, that's eating 1 plain. This next one is plain milk. Okay, that's eaten 1 plain. And the next one is plain. Well, that's not eating exactly 1, that's eating 2. So the ones we're interested in are the probability of the milk plain, okay, and the probability of the plain milk. So let's do the probability multiplying that we did before. 6 over 10 times 4 over 9. Okay, so that's 24 over 90. This one, 4 over 10 times 6 over 9, which is also 24 over 90. So the probability that I'm interested in, it is this one or this one. Okay, so the probability is 24 over 90 plus 24 over 90, which is 48 over 90, which if you pop that in your calculator, it cancels to 8 over 15. They would expect you to cancel that down. Okay, so can you see the difference between that one and your previous one? We've suddenly got the second event being dependent on what happens in the first event. And typically that is something like somebody taking a counter out and not returning it, or somebody taking something out and eating it. Okay, so one for you to have then. So I would like you please to write that down, okay, and to draw the tree, write the probabilities on the branches, and then do all the probabilities at the ends of the branches, and then work out the answer. So pause it, and then I'm going to go through it. Okay, so hopefully you have paused it. Let's look at what our tree diagram looks like. First outcome, picking the first sweet. Okay, 2 different possibilities, red, blue. Okay, that's sweet 1. Probabilities on your branches, 7 over 10 and 3 over 10. Okay, to get that right, you might have had blue on the top, red on the bottom. It really doesn't matter which order you put them. Second event, picking the second sweet. Again, we've got red and blue. Be careful about what the probabilities are though. Remember, the denominator always goes down by 1, so they're always out of 9. Red, there's 6 left because 1's been eaten. Blue, there's still 3 left because none of those have been eaten. Okay, happy with that? And then the final branches, again, you've got to think carefully about the probabilities. For this one, there's still 7 red left, but there's only 2 blue left because one of them, they have been eaten. So let's do all of the probabilities then. Okay, so we've got red, times along the branches, red, blue, times along the branches, blue, red, times along the branches, blue, blue, times along the branches. Let's see what the question says. What is the probability I eat 1 blue and 1 red? So that's just 1 blue and 1 red. Which ones am I interested in? Those pink ones. What do I do to them? Add them together. So I get 42 over 90 because it is this one plus this one. Okay, and then that cancels down to 7 over 15. So hopefully you got that one right. Okay, one last thing to show you. I don't know if you remember this from 2015 GCSE maths exam from the Edexcel exam board. It hit the newspapers, okay, because people were saying this was the first year of the new 9-to-1 GCSE, and people were saying it was an impossible question and how hard was that. Okay, so write down the question, we're going to have a look at it, and it's actually easily answered using a tree diagram. Okay, I don't know if you've heard of it. If you haven't, go and Google the famous GCSE maths question on sweets. Okay, it was all in the newspapers. Right, the only more difficult thing really is that rather than having a certain number of sweets in a bag, like 10, there's n sweets. So we've got to work a bit more generally. And I think that's why people found it quite difficult. Okay. At the end of the day, it's the same scenario as what we were looking at on our previous questions. We've got sweets in a bag, we've got some orange, we've got some yellow. Okay. We're taking a sweet, eating it, and then taking another one. So we're going to draw a tree diagram to help with this. Okay. So two different types of sweets. There's orange and there's yellow. Now think carefully when we fill the probabilities in. Okay, n sweets in a bag, so the probabilities are going to be out of n. Okay, that's the same as out of 10 if there were 10 sweets. Okay, 6 are orange, so I'm going to put 6 here for orange. How many are yellow? Well, I know they need to add up to 1. Okay, so that's going to be n minus 6. You don't actually make use of that bit anyway, so we don't really need to know that bit. Okay, let's go and do our next branches then, because she's eaten a sweet from the bag and then eaten another one. Okay, so our branches again are going to look like this, aren't they? Orange and yellow. Now, before I try and fill them all in, let's see what the question is interested in. The probability that she eats 2 orange sweets is 1/3. So the branches we are looking at is orange, orange. So actually, I don't really need to fill in the rest of the tree diagram. The main thing I need to fill in is what is the probability of this top orange branch. Right, she's eaten a sweet. So there's 1 less sweet left. So if the bottom was 10 in the first branches, I would just put 9. The bottom is n. So I need to take 1 away from it. Let's write it as n minus 1. Okay. What goes on the top? Well, there were 6 orange sweets to start with. She's eaten 1. How many left? 5. Okay. So I'm not really bothered about these. I'm not going to make use of them. Okay. So I'm not even going to bother filling them in. So here's the bit of information we now need to use. The probability that she eats 2 orange sweets is 1/3. Let's write down what the probability of orange is. What do? We go along the branches and we times together the probabilities. I know it's got some n's in it, but let's not worry about that for a moment, okay? Probability of orange is that times that. They've told us what it is. They've said it's 1/3. So we've now got an equation that we need to sort out a little bit because the question is show that, okay? This is two fractions times together. What do we do when we times fractions? Times the top, 5 6s are 30, times the bottom. I'm going to leave it in bracket like that. Now I want to get rid of my fractions in my equation there, so it looks more like this. Technique, remember, cross multiply. Okay, useful thing to get rid of fractions when you have one fraction equals another fraction. So you write that times that is equal to that times that. So you get n times n minus 1 is equal to 3 times 30, which is 90. Expand out your bracket and then bring your 90 over, and that's job done. The question then does go on, you're given a value, I think, for number of sweets in the bag, so then you've got to go on and work something else out. But that was the question that caused all that furore. So I think it goes to show really that if you are given a question, even if it's got some algebra in it or some letters in it, don't be afraid to draw a tree diagram if it's talking about two different events. It can often be helpful for you to work things out and for you to operate with your tree diagram in exactly the same as you would do if they had 10 sweets in the bag, say. Okay, right, over to you then. There is a tree diagrams worksheet which I've uploaded for you as well. So what I'd like you to do, you do need to print it out because it's something you need to write on. Okay, so print it out, write all your answers and working on the sheet. Any diagrams they do ask you to draw, to be honest, most of them they've sort of drawn some of them out for you, but any you're asked to draw them nice and neatly. show your probabilities, and then I've also uploaded work solutions for these, so just mark your questions against those. Okay, well, good luck with that. Thank you.